Okay, so tonight's session, per the schedule, we're going to be finishing up chapter 15, right? So tonight could be a short session, a little bit short. I really just want to finish up buffers. That's really it for chapter 15. We've already gone through titrations, so I might make like a note or two of that. But for the most part, we're just going to focus on buffers. And then there's going to be a time in case anybody has any questions, whether it's from chapters 15 or 14 or 13. Really, anything having to do with equilibrium is still relevant. So I'm happy to take any questions or clarify anything that people are still uncertain of. Hopefully, the exam last Friday went pretty well. It is typically seen as the hardest exam. Chapters 14, 15, 13, especially the multiple choice section regarding these chapters are typically the harder part. Chapter 15 we won't see until April 2nd. We'll see it in a long answer exam with chapter 16. But yeah, so here's our schedule for the next 2 weeks. So again, tonight we're going to finish our discussions of chapter 15. Then our next two sessions after that, we're going to be focusing on chapters 16 before doing a review of these two chapters to prepare for your long answer exam on Friday, April 2nd, which I think is Good Friday. Okay. So just before we get started, just a couple of things. I want to remind everybody that I do have office hours on Thursdays. I think it's listed 5 to 7, but it's by appointment. So honestly, I can be pretty flexible. Just, give me a notice ahead of time, email me. And I'm completely fine with it. I just got a lot of emails before the exam, Thursday night and Friday, pretty much all day. I was answering emails or doing my best to. And again, I'm there as a resource. I'm happy to do that. However, I felt like some people I could have helped a little bit more. And I just wish that, don't wait to the last minute is what I'm saying. Seek out help early, right? It's better to get help ahead of time than kind of waiting too long and not being able to get all the help that you want. Okay, so just a reminder, don't push off chemistry. I know with asynchronous classes, it can be a little bit easier to do, but, stay ahead of the game. If you want to meet with me this week for chapter 15 stuff, or even go back and do chapter 14 stuff so that you have a really good foundation for your next exam, I'm perfectly fine and happy to do that. But again, I just really wanted to make the note that, there's always help there. Try not to wait too long to seek it out. Beyond that, I think the only other comments I wanted to make was about the challenge problems. So kind of looking back, I had a little survey that I put on my page a little while ago. And a comment that I saw a couple times was about my challenge problems and how some people feel that they're more difficult than the exam questions at times. And people preferred for me to dial it back a bit. And what I kind of want to say on that note is I completely understand where you guys are coming from. And of course, if I knew what was on the exam and the difficulty of questions and the topics, I probably would cater my challenge problems a little bit more to the exam, right? But I'm going into all these exams blind, just like you guys. Of course, I have some experience under my belt where I know the topics they like to ask about how they like to ask the questions, about how many questions apply to certain topics. So I do have a general sense, but again, the professors don't tell me anything. And so my idea behind the challenge problems being difficult is at a certain point, me and the professors can only get students so far. We can help you review the material, we can give you practice problems and help you work through them. But on the exam, when you're taking it alone, right, and you face a problem that you don't know how to solve or don't even know where to begin, right, as a student, you need to build up the skill set of how to approach that problem, how to digest it, where to begin, especially in the stress of an exam, how to kind of calm yourself down and approach each problem logically. And so the idea behind the challenge problems is yes, sometimes they're going to be much more difficult than the exam questions, but my hope is that you take some time to try to solve these on your own, and that when you get to a point in the problem that you don't know how to continue, you kind of work through that to develop those skills so that when you get to the exam, you have some confidence in your abilities. And when you see a problem that you have no idea how to solve, you kind of just have the skill set to tackle that problem. Okay, and so that's why some of them may seem a lot harder than your exam problems. Again, I don't know how they're going to ask questions on the exam. I don't know what curveballs they're going to throw. And so I just try to throw my own curveballs to, again, help you develop those skills. And my last note before going on, I do really apologize. I do believe the strontium phosphate question, number 3, that I went over at the beginning of last session was wrong. Phosphate would be a weak base in that solution, and so I believe it would be basic. So I do really apologize for that. That's actually a question I've used for a little bit, and honestly, no one's really even talked to me or brought it up to me, and I know several students did, so I do apologize for really not catching that before releasing the question and going over it. Okay, so before we begin, does anybody have any questions or comments, concerns about kind of the things I just talked about a little bit? Okay. So if you're entering something in the chat, I'm just gonna, we're gonna go through 2 challenge problems tonight. They are both from last Monday's session, right? So it was problem 5 and 6 from last Monday, but these had to do with chapter 15, which is why I didn't go over them Wednesday's session, right? So I held them off. So number 5 is, which of the following weak acids and its conjugate would create the best buffer for a pH of 4.9, right? So you're given 5 different acids and given their Kas. Right, and so the key to this problem is a weak acid and its conjugate has a specific buffering capacity, right? So a buffer will work when for a certain pH if it falls within its buffering capacity. Okay, and so what we say is that the buffering capacity is the pKa plus or minus 1 pH unit. Okay, and so that's what I'm going to show on the next slide. So what I did is I took all 5 of these acids individually, and I wrote their Kas. And what I did is I found their pKas, right? So remember, to solve for the pKa, we just take the negative log of the Ka. Okay, so for lactic acid, I did the negative log of 8.3 times 10 to the negative 4th. That came out to 3.08, right? So the pKa for lactic acid is 3.08, and I wrote plus or minus 1. Which represents its buffering capacity. That means lactic acid with its conjugate can buffer in a pH range between 2.08 and 4.08, right? Plus or minus 1 from the pKa, right? So 1 pH unit below the pKa or above. And so I did that for all 5 acids that were given. And the pH that we were asked to buffer at is 4.9. And so when we look at all of our pKas and do plus or minus 1, there's only one acid whose buffering capacity includes the pH value of 4.9, which is benzoic acid, right? Its pKa is 4.19, which means it would be able to buffer between 3.19 and 5.19, okay? Now, when you look at all the other acids, their buffering capacity range, none of them include 4.9 besides benzoic acid, and so B would have been the correct answer for this. Okay, question 6 is a little bit more your classic buffer question. So we're going to make a buffer out of 35 grams of hypochlorous acid. The Ka for that is given. We're told that it's 125 milliliter solution, and it also includes 75 grams of calcium hypochlorite. Okay. And so we're asked, what's the pH of this solution originally? And then after that, we're going to add 18.5 millimolar barium hydroxide. And after that change, what is the new pH? Okay, and so what I'm going to start to do is I'm going to solve 4 moles of, sorry, it's kind of cutting off, so I can't actually read it, but I believe it's hypochlorous acid, right? So I take the 35 grams, I divide it by its molar mass, and then divide it by the volume to find the molarity, right? And so I find that my acid is 5.34 molar, which is also equal to 0.667 moles. Okay, and you'll notice here that I wrote both. And the reason for this is that whenever you do a buffer question, right, you can do it in terms of moles or molarity, right? You can choose, but as long as you're consistent, you'll get the correct answer. Okay, now that I know the number of moles or the molarity of my acid, I'm going to do the same for my conjugate base. Okay, so I'm going to take my 75 grams of calcium hypochlorite. Hopefully you remember that there's 2 molecules of hypochlorite per 1 molecule of calcium hypochlorite. Like it's a 2 to 1 so that the charges cancel because calcium has a +2 charge. I'm going to convert it to moles using the molar mass. Then I'm going to convert to just moles of hypochlorite. Sorry, kind of forgot the name. And then I'm going to divide by my volume to find what the molarity of that is, right? So in terms of hypochlorite, my solution is 8.39 molar. And again, if I wanted it just in terms of moles, it would be 1.05 moles. Okay, and so once I know my initial amount of hypochlorous acid and hypochlorite, I'm just going to write my equation, right? I always think writing an equation at the top is a beneficial way to start a problem. Okay, so again, hypochlorous acid will react with water to produce hydronium and hypochlorite. Okay, and I'm going to enter in my initial amounts. Now again, in my ICE table here, I wrote it in terms of molarity, but it would be equally correct to write it in terms of number of moles, right? You could have done either one. Okay, and so I wrote my initial amounts, and it's a buffer question, right? So in buffer questions, we're typically going to solve it using the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is pH equals pKa plus log of our base divided by our acid. And so to use this equation, I know that I'm going to need my pKa, right? And so I was given that my Ka for this acid is 2.8 times 10 to the negative 8th. So to find the pKa, I'm going to take the negative log of that number. And when I do that, I find my pKa is 7.55. Okay, so now that I know the value of my pKa and I know my amounts of hypochlorous acid and hypochlorite, right, I know those amounts, I can plug that into the Henderson-Hasselbalch equation and I would find that my pH comes to 7.75. Okay, now you might notice that I actually wrote the Henderson-Hasselbalch equation twice here. Okay, in the top one, I plugged in my molarities, right? So I plugged in 8.39 molar for hypochlorite and 5.34 molar for hypochlorous acid. And in the bottom one, right, I plugged in my number of moles, right? So 1.05 moles of hypochlorite and 0.667 moles of hypochlorous acid, okay? No matter which one of these you use, right, you will get a pH of 7.75, okay? And so I just wanted to show both ways because they will get you the same answer, and which, you know, using moles or molarity, it's just your preference. Okay, and so that's the answer to part A, 7.75 is our pH. Okay, moving on to part B, right? This is kind of a classic extension to a buffer question that not only do we solve the pH of our initial conditions, but now we're going to add a strong base and see how that shifts our pH. Okay, and so in this circumstance, I'm adding 18.5 millimolars of barium hydroxide. Okay, and so again, hopefully you know that in barium hydroxide, we have 2 hydroxides per 1 molecule of barium, or 1 atom of barium. And so in terms of just hydroxide, I actually have twice the initial amount, right? I actually have 37 millimoles of hydroxide. Okay, and millimoles is just 1/1000th of a mole. Okay, so 37 millimoles is really 0.037 moles of hydroxide. Okay, now if we divide this amount by our volume, like we did above, so we divide it by 125 milliliters, we would find that 0.037 moles of hydroxide is equivalent to 0.296 molar hydroxide. Okay, and so now I'm going to write my ice table, and the amount of hydroxide I added is going to represent my change. Okay, and the whole idea of a buffer is that we are going to resist pH changes, right? So the amount of hydroxide that we added, we're going to see a shift in our equilibrium to neutralize all of that hydroxide. Okay, so for my change section here, I'm going to have plus 0.296 molar on my product side. And the reason for this is I want to make 0.296 molar hydronium, which will neutralize all of my hydroxide, right? They'll combine and form water. Okay, so they're going to completely neutralize each other, which is how I know it's going to be plus 0.296 on my product side and minus that amount for my reactant side. And so at equilibrium, I would have a concentration of hypochlorous acid equal to 5.044 molar, and my conjugate base would have a concentration of 8.686. Okay, and so now that I have equilibrium amounts of my weak acid and conjugate base, I can plug them into the Henderson-Hasselbalch equation to find my new pH. Okay, and so in this case, pH equals my pKa, which is the same as above, 7.55, plus the log of my conjugate base, right? So at equilibrium, that concentration is 8.686, divided by my concentration of weak acid, 5.044. And so when you solve this, you would find that the pH comes out to 7.79. Are there any questions on these two problems before we move on? I'll just wait a minute in case there are questions. Okay. Then I will move on. And again, if questions appear, I'm happy to go back and discuss these further. Okay, so in terms of actual notes, these are the same buffer notes that you would have already taken. Really, in terms of buffers, we're just going to go through 2 new example problems, okay? But the actual physical notes on buffers aren't going to change. Okay, so again, remember that buffer solutions can resist not only the addition of H plus or acid, protons, but it can also resist the change in base or hydroxide added. Okay, so we're always only going to add strong acids or strong bases when we have a buffering system, right? So we're going to have the buffering system between a weak acid and its conjugate, and then into that, we're going to add either strong acid or strong base, right? That's a very common type of question, and one that we just did before, right? In the last problem, we added strong base barium hydroxide. Okay. Now, buffers have a requirement. They not only just need a weak acid, but they also need the conjugate. Okay, they need both. Okay, it's not enough for just one to be present. Okay, and so we see 2 different forms of, the creation, or 2 different ways that buffers are created. I would say the more common way is this first method, this first method, where we're given a weak acid and then the conjugate base is added as a salt. Okay, and so in the last problem, right, we had hypochlorous acid, a weak acid, and then the conjugate, which was hypochlorite, was added as a salt, right? It was added as calcium hypobromite. Okay, so it's realizing that that calcium isn't actually taking part in the reaction. The only use for it is it allows us to add our conjugate weak base. Okay, so that's the typical way, or the more common way you will often see buffers being created. The other way we can see a buffer solution being created is by partially neutralizing a weak acid or base with a strong base or acid, right? So this point where we partially neutralize a weak acid or base, this in our titration problems would correspond with before the equivalence point. Okay, so whenever we're doing a titration problem and we identify the scenario as before the equivalence point, right, that solution that you create from that part of the titration is a buffer system, okay? And we'll look, one of the examples tonight that we'll look at is the creation of a buffer through the partial neutralization. Okay, so some key points about buffers. So remember, a key component of this is the neutralization reaction occurring, right? If we're going to add hydroxide to our equation, right, our equilibrium is going to shift so that we make more hydronium or H+, right? You're going to make more acid components because they're going to neutralize each other and form water, right? If you add strong acid to a buffer system, right, your equilibrium is going to shift so that you create hydroxide, which the purpose of that is, again, to neutralize the acid added. Again, that's how it resists the pH changes. Okay, these little bullet points, if they're helpful for you, they're helpful, but I think I have a drawn out version on the next couple slides that might be more helpful. But these two little bullet points are just talking about the change section and how you know whether it should be minus X or plus X. Okay, and again, the last point for this is something that we exemplified in problem number 6 on the challenge problem review. Right, our acid and conjugate are in the same solution. So if you want to put your ice table in terms of moles, that's completely fine. If you want to put your ice table in terms of concentration, that's completely fine. As long as you stay consistent, so your acid and conjugate are both in moles or both in concentration, right? As long as you stay consistent, you should get the correct answer. Okay, and so we said that buffers can resist the addition of hydroxide or H+, right? The addition of strong base or strong acid. And so you might ask yourself, how do we do this, right? And so when we add hydroxide, that's going to react with our weak acid portion to create water and our conjugate base. Okay, so whenever we add hydroxide, really, by shifting the equilibrium, what's going to happen is your weak acid is going to react with that hydroxide to form it into water, and we're going to form more conjugate base when that happens. Okay, now when we add protons, or we add the acidic portion, right, that'll combine with our conjugate base section, and them combining will cause us to form more of our weak acid. Okay, so the addition of base causes us to form more of the conjugate base. The addition of acid causes us to form more weak acid, right? This is just how our equilibrium shifts. Okay, but really just note that, again, through these two mechanisms, it can resist the addition of both hydroxide and H+. Okay. And so how does this correlate to when we actually are doing problems? Okay, so because buffer solutions contain both our weak acid and our conjugate base, right, we can actually write the same buffering system through two different equations, right? And so whichever one you prefer is fine, you will get the same answer, but just note that you can write them in two different ways. Okay, so the first way you could write your equation is you could react your weak acid portion with water, and on the product side, you will have hydronium and you'll have your conjugate base. Okay, now what happens if to this buffering system you add X amount of strong base, right? X amount of hydroxide. Well, the whole point of buffering or buffer systems is we want to neutralize this hydroxide. Okay, so if we add that amount of hydroxide, we're going to shift our equilibrium to add that same amount of hydronium, right? Because they're going to combine to form water. That's the neutralization reaction. Okay, so if this is your equation and you add X amount of hydroxide, you're going to add that amount, that X amount, to your product side, and you're going to subtract it from your reactant side. I know that's kind of I think I started to write a plus. That's a minus. Okay, so be sure that you know that. You would subtract it from the reactant side and add it to the product side. Okay, now what happens if you have the same equation, but instead of adding base, we add acid, or H+. Okay, now we know that to neutralize this H+, we want to form hydroxide, or OH-, again, so that neutralization occurs. But when we look at our chemical equation, we don't see hydroxide, right? Instead, we see hydronium. Okay, so if you add H+, and H+, or H3O+, again, they're the same thing, is in your equation, the amount that you add, so if we added Y amount of H+, we're going to subtract that amount from hydronium. Okay? We're going to subtract that amount from hydronium and the other products, and we're going to, sorry, I completely messed up my signs here, and I wrote it just across the board. This should be plus Y right here. So it would be plus Y on the reactant side and minus Y on the product side. Okay? And so if we add H+, and H+ is on our equation, we're going to subtract that amount, and we're going to add it to the other side. Again, I really apologize about that sign mistake. I fixed it on this slide. Okay, so as I said just a couple of minutes ago, we can actually write these equations in two different ways. So on the previous slide, I started on my reactant side. I reacted my weak base with water. Sorry, weak acid with water. In this slide, I'm going to write my equation where I actually start with my conjugate base, my weak base. I'm going to react it with water to produce a weak acid and hydroxide. Okay? Understand that the equations on this slide and the last slide are the same thing. They describe the same exact buffering system. There's just two different ways of writing it. Okay, so if you prefer to write your equation in this way, let's look at what happens when we add acid or base. Okay, so for this first example, let's pretend that we added X amount of hydroxide, right? So we're adding base. Now we know that we'd want to shift our equilibrium in order to create equal amounts of hydronium compared to hydroxide. Okay, but again, in this equation, we don't see any hydronium or H+, right? So we can't do plus X for that. Instead, in this equation, we have hydroxide. So because we're adding hydroxide and hydroxides in our equation, right, our change for our hydroxide is going to be minus X, or minus the amount of hydroxide added. Okay, so in this case, we would subtract X from our product side and we'd add it to our reactant side. Okay. On the contrary, if we want to add Y amount of acid, or H+, right, again, we want equal amounts of hydroxide and H+ to neutralize each other. So that indicates to me that for my change for hydroxide, I want it to be plus Y, or plus the amount of H+ that I added. Because again, if there are equal amounts of that, they're going to neutralize each other, which is the whole goal of buffers. Okay, so that's how I know it should be plus Y for the products, minus Y for the reactants. Okay, now again, whether you prefer to write it how I did on this first slide or how I did on the second slide, you will actually get the same exact answer, right? Because your equilibrium amounts of weak acid and weak base will be the same, whether you use the first equations or the second set, okay? And so again, just realize that they're the same, and I don't know, make sure that you're comfortable with knowing what side should be plus or minus, X, depending on if you added base or acid. Okay, are there any questions on this before we move on? And if there aren't, if people can just take a moment to indicate that. Okay. Awesome. Thank you, Asid. Okay. And so again, the equation or the way you choose to write the equation is up to you. Whatever you feel most comfortable with, just realize that they're the same thing. So either way is equally correct. Okay, so again, kind of the last notes, again, these are something that I've given before, is that when we do buffer questions, right, we'll always have some amount of weak acid and our conjugate, right? And so anytime, and this is outside of buffer questions, but buffer questions will always apply to this, anytime we have weak acid and the conjugate, and they're both present in the solution, we can use this Henderson-Hasselbalch equation. Okay, and so for buffer questions, we can use this equation for just about every problem. Okay, and I do recommend you utilize this, which I think that's how your professors are, all of them are teaching it this semester. So hopefully you are very familiar with this equation by now. Okay, and then just some notes on the effectiveness of a buffer. And so we say that a buffer is going to be more effective if it has more buffer components, right? So if you have two solutions and one has 1 molar of weak acid and 1 molar conjugate base, while the other solution has 0.1 molar weak acid and 0.1 molar conjugate base, the one with the 1 molar of each component will be the better buffer. And the reason for this is just the larger your concentrations are for your acid and your conjugate base, that just means that you can physically resist the addition of more acid and more base. Okay, so the higher the concentrations, it just means you can neutralize even greater amounts of acid or base. Okay, and we also have what we call a buffering capacity, right? So every buffer system can really only buffer a specific range. And we say that that range is the pKa plus or minus 1. Okay, so this again kind of touches back to the question 5 that we went over at the beginning, right? The buffering capacity would be 1 pH unit higher or lower than that pKa. And a buffer is most effective when the concentration of acid and conjugate base are identical, right? So a particular buffering system will do the best job at buffering when the pH is equal to the pKa, right? Which is, it would also have equal amounts of conjugate base and acid. Okay, so moving on from kind of the theoretical notes, let's look at some example problems. Okay, so here we're gonna have 350 milliliters of a buffer solution, and it has 0.8 molar hydrofluoric acid and sodium fluoride. Okay, so we know that the amount of hydrofluoric acid is 0.8 molar, but we're just told we have sodium fluoride. We're not given an amount. Okay, it tells us that the pH of this solution is 3.90. And so based on this, what would the mass of sodium fluoride be in order for this buffer described to be made? Okay, so here, right, we're not using the amount of acid and conjugate base that we have to solve for pH. Instead, we're actually working backwards, right? We're going to be using our pH to work backwards and find how much sodium fluoride we actually started with. Okay, and so we're also given a Ka here. Okay, and so again, we were given a pH. Now, given that this is a buffer question, I have a pretty good feeling, right off the bat, that we're going to end up using this Henderson-Hasselbalch equation. Okay, and so again, a key piece to this Henderson-Hasselbalch equation is that we require the pKa. Okay, and so that's what I'm going to start with. I'm going to first solve for my pKa. So my pKa is equal to the negative log of my Ka, and my Ka was given in the problem. It's 6.6 times 10 to the negative fourth. Okay, and so when I do that calculation, the negative log of that value, I find that my pKa is 3.18. Now that I have that value, I'm going to start plugging in all my known numbers into the Henderson-Hasselbalch equation. Okay, so my pH, which was given in the problem, was 3.9. My pKa, again, is 3.18. And we're going to add our pKa to the log of our base, which we don't know how much of our conjugate base F minus we have, divided by the amount of acid we have, which was 0.8 molar. Okay, so realize that I'm plugging in molar in terms of my acid, which means when I solve for F minus, or the amount of F minus, it is going to be in terms of molarity. Okay, if I preferred to plug in moles instead of molarity, that also would have been fine. Okay, and so from here I do a bunch of algebraic manipulation, right? I subtract 3.18 from both sides. That gives me that 0.72 is equal to the log of F minus divided by 0.8 molar. To get rid of this log, we're going to do 10 raised to the other side, right? So 10 raised to the 0.72, right? This is the exponent, is going to be equal to concentration of F minus divided by 0.8 molar. Okay, so 10 raised to the 0.72th power is 5.25. And when I solve for just my molarity of F minus, it comes out to 4.2 molar. Okay, and so from here, I'm just going to kind of do my normal stoichiometric calculations to find how many grams of sodium fluoride this was. Okay, and it really is important to note that it's the mass of sodium fluoride, okay, not just the mass of fluoride. Okay, so this solution has a volume of 300 milliliters. So I'm going to convert this to liters. So 1 liter is 1,000 milliliters. And now that I have my volume in terms of liters, I'm going to multiply it by the molarity we just solved for, right? So the molarity of my fluorine, my conjugate base, is 4.2 moles of fluorine per 1 liter of solution. Now that, if you cross out all your units, now that we have moles of fluorine, I'm going to convert it to find moles of sodium fluoride, right? So 1 mole of fluorine is 1 mole of sodium fluoride. And then 1 mole of, I wrote HF here. Oh, is that the wrong? This molar mass might not be right. And so I know that's not right, that molar mass. So I apologize for that. I wrote HF, I meant NaF. And so the molar mass here would be wrong. But when you undergo the basic calculations are correct. You should just do 1 mole of NaF is, I think it would come out to, the molar mass would be about 42 grams per mole. So I do apologize, but if you plug in 42 grams per 1 mole NaF, you should get the correct answer. So again, I do apologize. And I'm plugging into my calculator to see what that would be real quick. Okay, so besides my error, are there any questions on this problem? I get that it would come out to slightly below 60, or right around 60 grams. Okay, so again, I apologize. That was a brain fart. Okay, but any questions on this part? And if not, if you don't mind right now in the chat, just putting in your net ID to sign in, that'll kind of indicate to me that you understand this problem and are ready to go on to our second example. Okay. So I think that's right about everyone or very close to it. So again, just to reemphasize, this last molar mass was wrong. It's supposed to be 1 mole of NaF, and it's about 41, 42 grams per mole of that. And so if you just go through this dimensional analysis with that updated number, it should give you the correct answer. Again, I just blanked there, so I apologize. Okay. So let's look at this second example. Now, this is one where we're going to create a buffer by partially neutralizing a weak acid. Okay, so in this system, we're again going to have hydrofluoric acid, right? So HF, its concentration is 1.3 molar, and we have 200 milliliters of it. Okay, now to this, we're going to add 120 milliliters of 0.75 molar barium hydroxide, right? A strong base is being added to weak acid. And so part A is this a buffer? And what is the pH of this solution? Okay, and then part B, we're going to say that we added too much base, right? We added too much barium hydroxide. And so we're going to add 0.15 moles of hydroiodic acid. And based on that, what would the pH be? Okay, so remember that when we say a buffer can be created by partial neutralization during a titration, right? That's referring to the situation that I call before the equivalence point. And this can occur through two different titrations, right? We can have, if we have a weak acid being titrated by a strong base, we will have this partial neutralization when we have more moles of our weak acid than we have of strong base, okay? Or under the circumstance that we have a weak base being titrated by a strong acid, we partially neutralize, we have partial neutralization to create a buffer whenever we have more moles of weak base than moles of strong acid. Okay, so really, anytime that you have more moles of the weak portion compared to the strong portion, you will have a buffer in this partial neutralization. Okay, and so let's kind of prove this, right? So we have 125 milliliters of 0.75 molar barium hydroxide. And so I multiply these together after converting our volume to liters to find that we have 0.09 moles of barium hydroxide. Now, we don't really care about the barium part, right? We only care about the hydroxide part. And we know that strong bases dissociate completely. Okay, so by saying we have 0.09 moles of barium hydroxide, we're really saying that we're adding 0.18 moles of just hydroxide, right? Because we have 2 moles of hydroxide per 1 mole of barium hydroxide. Now that we know the amount of hydroxide added, I'm going to find how many moles of acid we have. Okay, and again, here's a little error. That's supposed to say moles. For some reason, I keep forgetting to write moles. I'm just writing molarity. I did that on lots of problems, and I found quite a few of them, but I did miss this one, right? So 200 milliliters or 0.2 liters of 1.3 molar HF is 0.26 moles. This is supposed to say moles. Again, I apologize for that, of hydrofluoric acid. Okay, so now that we have our moles of weak acid and moles of hydroxide added, right, we can compare them. Okay, and I can see that I have more moles of weak acid than moles of hydroxide, meaning we're going to have partial neutralization of our weak acid, which means a buffer system will be created. So I'm going to make an ice table for this situation. So I'm going to have my hydrofluoric acid, which reacts with water to produce hydronium, and my conjugate base. Okay, and my initial amount of hydrofluoric acid is 0.26 moles. Again, up here, that's supposed to say moles, not molar. Okay, now for the change section, right, remember that we're adding 0.18 moles of hydroxide. And so during titrations, we want to neutralize this hydroxide. So we're going to neutralize it by shifting to the product side, right? We're going to shift to the product side and create 0.18 moles of hydronium so that it can neutralize all of the strong base that we added. Okay, so plus 0.18 to the product side, minus 1.8 from the reactant side, and at equilibrium, we're gonna have 0.08 moles of acid and 0.18 moles of conjugate base. Okay, now that we have these amounts, right, and thinking ahead to the Henderson-Hasselbalch equation, I know I'm gonna need my pKa. So knowing that my Ka is 6.6 times 10 to the negative fourth, I can find my pKa by taking the negative log of that value. So my pKa comes out to 3.18. Okay, so I'm going to write my Henderson-Hasselbalch equation. pH equals pKa plus log of my base divided by my acid. Okay, and so I'm going to plug in my pKa, 3.18, and I'm going to plug in my equilibrium amounts of F minus and HF, which is 0.18 moles and 0.08 moles respectively. Okay, again, for this equation, I decided to plug in moles. If you wanted to convert to molarity and plug that in instead, that would be equally correct, but you can do either one. Okay, and so when I plug in these values to my equation and solve for pH, my pH of this solution comes out to 3.53. Okay, so that would be the answer to part A. Yes, this is a buffering system because we had more weak acid that was partially neutralized or partially counteracted by strong base, right? Only part of it was neutralized, and yeah, and the pH, which was the other part of the question, is 3.53. Now going on to part B, right, we said that after part A, our solution was almost too basic. So instead, we decided to add an additional 0.15 moles of hydroiodic acid, which is a strong acid. So by adding 0.15 moles of HI, I'm really adding just 0.15 moles of H plus, right? Because hydroiodic acid will completely dissociate as it's a strong acid. And so what I do is, again, I write my ice table and I write my initial amounts based on my equilibrium amounts from part A, right? So at equilibrium in part A, I had 0.08 moles of HA and 0.18 moles of my conjugate. Okay, now my change, again, I'm adding 0.15 moles of H plus. Now in my equation, I don't have any hydroxide. Instead, I have hydronium, which is the same thing as H plus. So because I'm adding H plus, and H plus is in my equation, my change for hydronium is going to be minus the amount of H plus that I add. Okay, so that's how I know that for the products, I should have minus 0.15 moles for my change. And for my reactants, it should be plus 0.15 moles. Okay, when I do that math at equilibrium, I can find that I have 0.23 moles of my weak acid, which is hydrofluoric acid. And at equilibrium, my conjugate base, which is F minus or fluorine, I would have 0.03 moles. Okay, now that I have these new equilibrium amounts of my acid and my conjugate base, I'm going to plug them into the Henderson-Hasselbalch equation, and I'd find that my new pH is approximately 2.3. Okay. Okay. And that's the last example that I have for tonight. I do have some challenge problems, but I just wanted to kind of take this time to answer really any questions that you have, especially on chapter 15, buffers and titrations, but I'm also completely happy to answer really anything that has to do with equilibrium, any remaining questions. Okay. If nobody has questions, again, just if a few people can indicate that in the chat, that'd be great. But I do want to take this time to really make sure that these topics make sense. So Lizzie asks, is chapter 15 just titrations and buffers? And I would say yes. So back when I took the course in the old textbooks, buffers and titrations was in chapter 14 with our acid-base equilibria. But I did today make sure that I reviewed all the videos from chapter 15, and really the only thing covered was titrations and buffers. The only thing I didn't really go over tonight was indicators, which was kind of just a couple of short slides in the lecture videos, but I've previously gone over that in SI, so I didn't want to re-go over those. But I would say it's really just titrations, buffers, and indicators from lecture at least. So yeah. Any other questions? Okay, awesome. Okay, well, again, at the end, I'm also happy to stick around to answer any questions. I can also pull up old PowerPoints if people want to ask about something from a previous SI. Awesome, thank you guys. Okay, so tonight I'm gonna give 6 challenge problems. I've kind of said this since the beginning of going over buffers and titrations that students, in some ways, these are difficult problems, but the nice thing about these topics is that your professors don't typically give you curveballs, right? These topics, because they're more difficult, the professors tend to ask slightly more straightforward questions. Okay, so how I've worded my titration questions in the past is pretty much how they're seen on the exam. Okay, and so what I wanted to do tonight, however, is try to come up with some curveball questions regarding buffers and titrations. Okay, so again, typically there aren't crazy curveballs thrown at you, but in case there are, I want to give you some exposure to some abnormal questions relating to these topics that you guys, based on the information you have learned, can solve it. But again, they're a little bit more outside the box. They're definitely going to take some more critical thinking. And so these are actually some of my more favorite challenge problems, these 6 I'm giving out tonight. Okay, so this first one's actually an activity. So when we do titration questions and we go through the situation that I call past the titration point, right, we don't do a reverse ice table. Right, we only do a reverse ice table, or at least that's what I call it, when we are at the equivalence point. Okay, now Dr. P in his lecture kind of proved why you don't need to do a reverse ice table when you go past the titration point. And so the first question is more of an activity, and it's kind of proving why you can do that. So based on this titration, or this scenario of this titration, I want you to solve it 2 ways. The first way, you can do it how I normally teach how to solve it, right? Solve for the pH that way, where you are just going to have excess hydroxide. You're going to solve for the concentration of that and then find the pH and the pOH. And then through the second mechanism, or the second avenue, I actually want you to do the reverse ice table. And I basically just want you to prove to yourself that even if you do the reverse ice table in the scenario that you're past the equivalence point, right, it's a negligible amount. Okay, so again, this is something that I believe it was Dr. P in his first lecture video for chapter 15, I think it was, or maybe the second. He actually kind of proved this, and I really liked that activity. I think it was helpful, so I created a situation for us to do the same. Okay, and please clarify if that didn't make sense, what I was trying to say here for you guys to do. Please just let me know that. Okay, questions 2 and 3 are based on a titration curve, which is shown in the top corner, right? So our y-axis is our pH, and our x-axis is really just amounts. It's our volume in terms of milliliters, but basically it's the amount of hydroxide we're adding, right? So as we add more and more hydroxide, our pH is going up and up and up. And so question 2 is based on the titration curve. Which acid does this represent? Okay. And the second one, or part 3, which is the second question based on this graph, is based on the titration curve, at approximately what pH values can you buffer a solution, right? So basically, what's the buffering capacity or buffering capacities, if there are multiple, for the acid shown in this titration curve? Okay. Moving on. Example 4 asks which of the following is not a buffer. So again, this is similar to examples that were gone over in lecture. Basically, you were trying to analyze which one of these can be a buffer based on partial neutralization of a weak acid or weak base. Right, so that's kind of the key to this problem. So it's which of the following is not a buffer. Only one of them will not be. Moving on, question 5 is a buffer question. It is possible, but it is a difficult question, right? Number 5, I think, is more difficult than you would typically see. And so here, you're actually given, after you're given initial amounts of acid and conjugate, right? You're given that you want to make a solution with a pH of 4. And so you're asked, should you add acid or base? And after you know which one, how many moles of acid or base should you add in order to get the desired pH of 4? Right? This is about one of the hardest buffer questions you could see in this course. Right? I don't think I've actually ever seen one of these asked before. Okay, but if you know or are able to solve question 5, I think you have a really good understanding of buffers up to this point. Right, so a great question to try. And then lastly, 6. So 6 is my attempt at a curveball for a titration question, which again is titrations are in this course kind of the most straightforward topics. Again, you see the least number of curveballs thrown on this type of problem. However, again, I tried it. So here we have 450 milliliters of 0.4 molar solution, and this solution is of an unknown acid, right? And so we're going to titrate it with 150 milliliters of strong base to reach equivalence point. At equivalence point, the pH is 8.67, and so based on this information, is our acid a strong acid or a weak acid? I want you to justify your answer, so how do you know it? And then in the scenario that if the acid is weak, what would the Ka of that acid be? Okay, again, question 6, this is a very hard question and shows understanding of titrations on multiple levels. And so again, I really highly encourage everyone to try this on your own. And even if you get stuck, really try to work your way through it. I'll be honest, even making this problem had quite a bit of work to it. And understanding. So I know that number 1, like number 6, would be very, very difficult. However, again, if you can work your way through it, I think you're in a very good position in terms of titrations. Okay, and that's all I have for tonight. So I'm going to end the recording. And wow, I actually ended almost perfectly in an hour. So I'm going to end the recording here. But if anybody has any questions, I'm happy to stick around and answer.